I am leading this analog panel, not because I recently did analog work, because that's some 9 years ago now, but for several years, starting in 2004, I was involved with the Mars Desert Research Station and later on also with the Flashline Mars Arctic Station. That was the moment Kim and I worked very intensely together, although we did so before, I think, because she was the person, truth be told, who would torture crews. I mean, there's no other verb that's appropriate here. Torture crews by her. You can only eat what I send you experiments. And then me in mission support had to deal with people being really grumpy. So, okay. Anyway, so for years I did that. I became the mission director of these stations. I was the logistics manager and the Capcom that cycled through the Martian day rhythm with that crew in at Devon Island. And it was wonderful. And then in 2010 we started Explore Mars, so I left the Mars Society, I left the management of the analog stations, and I started this big experiment on Earth, getting us all to Mars. So that's about me, and that's why I am I was designated as the panel moderator. Now, talking about Kim, like I said, we work together. She would be, together with Gene Hunter, would figure out what these simulated astronauts were supposed to eat. Partly she was completely right, because there's one thing I need to tell you. I once told Chris McKay, not the first person, if we're talking Mars research, that if he was on the station, on the Mars Desert Research Station, when the reports would come in the end of the day, without going to look at the menu yet, that was always the last report I would read, I could actually tell whether these adults, because they all were, at least over 80, many, now over 36 or so, and I could tell from their reports how they would manage little or bigger mishaps, whether they ate whole grain or not, or lots of sugar. If you're a parent or you're a cousin, you're an aunt or an uncle, and you have seen small children, you've taken them to the zoo or some other amusement park, they can get really upset and cranky when you have given them all these sweets, these ice creams, etc. And as an adult, you kind of know, you shouldn't do that because that's inviting disaster. You're inviting disaster if you do that. If you let adults just eat what they like. As well. I'm serious. And it doesn't matter whether you're a very experienced person, like Chris McKay, who's done, gazillion expeditions. Still, if you don't eat healthy foods, with slow carbs and not too much sugar, I can tell before I look at your menu. So in that sense, Kim was certainly right that you need to experiment what's the best food. Now, Kim, of course, she branched off and she started, doing a research station at Hawaii. Much nicer environment as far as I'm concerned than Utah. Utah isn't bad. But, if you have to choose a holiday to Hawaii or Utah, I think the choice is rather simple. Unless you're a very dedicated geologist or, then Hawaii is fine. But, unless you like dinosaurs, then of course you go to Utah.
I need to be very clear. The Hawaii that we're in is not the Hawaii you see in the travel brochure.
No. It's high up the mountain. Still. It's the idea that counts. You have to fly into Hawaii to get to the... And you will tell us later whether any of your simulated astronauts were really disappointed about the Hawaii they found and the Hawaii they thought they were going to. Then Jennifer, again, someone with a lot of interest, of course, in Mars and in, Moon and what do you do with the in situ resource utilization? If there's water ice, can you use it for water? Oxygen, all the other things. Truly analog field research, lots of it, and that certainly helps. You led quite a lot of teams, I think. That must have been interesting, I know from experience, especially if there are, I think if you lead scientists into the field, it's like herding cats. Yeah, right. Yeah, that's yeah. So it doesn't matter whether you do that in Utah or in Atacama Desert. Yeah, okay. I thought it might have done something with the environment, but apparently that doesn't help. And of course, Jennifer is involved with the future human exploration of Mars. Then Natalie has enormous experience at Johnson Space Center, which for all of us, of course, Space Center, Johnson Space Center, and that's human spaceflight. That's where they think about how to do things out of Earth's gravity well, whether that's ISS, Moon, or later on Mars. And you have a lot of experience with the exploration spacesuits. And anyone doing analogs, even if we do mock-up spacesuits, that spacesuit in reality will be a deal breaker for how much we can do outside, how versatile our hands will be, how easy we will trip or not trip. So that's really, really important. Then Julie Robinson, chief scientist, NASA Johnson Space Center again. So again, the place where exploration and how to do it right with humans, especially with humans, is done. You are someone who really gets the ear of the leaders, and I commend you for that. That isn't easy, I think, in this big conglomerate that NASA is. And you have worked for International Space Station, simulating Mars missions, and very important, what does the extreme environment do for human health? Because it's not just going up there and going down. It's not 3 days to the moon. If we go to Mars, Leonard David just said 8 months. Others say 8 months. I always hope that we go in a time when there is a short commute, and so that's 6. But still, it's a long time. 6 months. How do you keep humans in space healthy? How do you keep the risks low? If not, then there will be no successful human exploration beyond Earth orbit. Is it simple as that? We can dream, but then it won't work. Now, I propose that Kim is the first to handle her talk and tell us, what struck you most in doing these simulations.
Thanks, Artemis. So yes, I think my slides will come up in a moment. We've now done 6 missions at HiSEAS, 2 4 months, 2 8 months, 1 12 months, and another 8 months that got started but had to be called short due to an accident at the habitat. So it's 5+ years of experience doing this now, and many, last count we had something like 40 months of active mission time at the habitat. So just to point out some of our specialties there, one of the things that's really important about analog research is to match the research question to the analog. So if you have your research question, find an analog that's appropriate for it, because they're not all appropriate for everything. HiSEAS, which I'll show you in a moment, is Earth-based. So if you want to do experiments on countermeasures to Earth's gravity, it's not a good place to do it. If you're interested in people genuinely feeling the experience of their lives being in danger, it's also not a good place to do it, because in their heart of hearts, people at HiSEAS understand that there's a hospital a fairly short distance away. However, if what you're interested in is some of these issues to do with the distance of Earth, such as very long duration missions and how things change over months and years, if you're interested in isolation, having a small group of people physically isolated from the rest of the human population and stuck with each other for these long durations, and if you're interested in psychological health, how it varies over time, and how the delay in communications could affect interacting with mission support or ground control, whatever you want to call it, then a place like HiSEAS is a very good place to investigate some of those questions. So I think that's a theme that will probably come up with the others, that there is no perfect analog for Mars except Mars. And so if you really do have to make sure that you're picking the right questions. This is HiSEAS. HiSEAS stands for Hawaii Space Exploration Analog and Simulation. You will notice none of those letters are M for Moon or M for Mars. We think that it's an analog that's useful for a variety of mission profiles. Again, our specialty is really these long duration missions. If you look at some of the other analogs in Antarctica or underwater or in Utah, it's because either they're very, very, very isolated or because they have big seasonal changes, it's harder to do these consistent many-month missions. So as you can see, this is not the Mars in the tourist brochures, or the Hawaii in the tourist brochures. It is fairly Mars-like in geology, not quite as Mars-like as Hank was pitching it, but still it does have some of the features you'd expect to find on the Moon or Mars, in particular lava tubes. And also there's very little visible life. You'll occasionally find a small plant or a spider or something like that, but there's not sort of macro life wandering around. And you're visually very isolated. You can't see human activity, really. The only human activity that is really visible is up here on the top of Mauna Kea, which is the facing mountain. You can see the telescopes that are up there off in the distance. But they kind of look like something you might expect to see on Mars anyway, so it's not that disruptive. It's off the grid. Most of the power comes from these solar panels, which are stored in some very sexy batteries, and it's a sign that I've been doing this too long. I think batteries are sexy, but they are. And so it's completely isolated. It's not closed loop. This is not a real sealed dome. The idea, though, is that it allows our crew to suspend the disbelief and understand that when they go outside, they have to have the spacesuit on before they go. This is obviously we don't have a clear dome, but it gives you some idea of the layout inside. So we've got the ground floor, which is the kitchen, a flexible use area, and a laboratory. And then upstairs are where the bedrooms are. They're very, very small, sort of pie piece sized, and not that much bigger than one of these tables. But it is a private space. They do have doors that shut and critically lock. What else can I tell you about that? It's a pretty good start. There are 2 toilets. They're both composting toilets, relatively high-tech composting toilets, but anyone who has ever had to manage a composting toilet, if the microbial community in them is happy and healthy, then what you get out as the end product is fairly clean and pleasant smelling compost. If that community is not healthy, you get out what you put in. And so our crews, they go in with all sorts of academic backgrounds, but they all come out microbiologists because they are motivated. So I mentioned the lava tubes. This is one of the things that on the Moon or Mars, people are going to be interested in investigating, both as science sites and as potentially as shelters, since the ceiling of the lava tube provides very good protection against radiation. I think if you've been to see a lava tube at a park, you have probably been to see one which was pretty easy to get into and out of. Sometimes the rubble will have been cleared, sometimes there's stairs, or it was just chosen to be a particularly easy access one. As you can see here, it's not always that easy to access. This is a pretty typical skylight into a lava tube, and it takes some pretty significant clambering to get into them. So one of the things that our crews do when they're out on EVAs is explore the lava tubes and map them out. And then I don't want to take up any more time, but I did want to share one thing to you. 2 things. One is we've got a member of our first crew here. Yahida, you want to wave your hands? Yeah. So if you have any questions about what it's like to actually be a crew member, she'd be a good person to ask. There's another one here at the meeting somewhere, but I don't think he's here right now. The other thing is that our longest mission was 12 months, and at the end of the 12 months, we were really honored to get a tweet from President Obama saying, congrats to NASA and the scientists taking us a step closer to Mars. Now enjoy Hawaii and get a shave ice. So we followed that presidential command and got the crew shave ice. Then we did another 8-month crew with our current president, and I'm almost as proud to say we didn't get tweeted. So that's it for me, and now who is next?
Julie? Okay, well, thank you very much, and thanks, Artemis, for having me included in your panel. One difference between the things that I'm going to talk about today and some of the other panelists is that I actually want to talk about the continuum. There should be some charts. Yeah. Is that there's really a continuum between the things that we do on Earth, the things that we do on the International Space Station, the things that we will do on Gateway and on the lunar surface. All of those are, in essence, a kind of an analog for a Mars mission, each one with fidelity in different areas. Looking in the back, you seen the charts back there?
I'm going to, you talk, I'm going
Okay.
to try whether I can
Great.
fix it. I was the engineer at both of the groups.
Okay,
Yay!
Okay. Yeah, let's, oh, that's us. Okay. That's not us.
No.
They'd be labeled Robinson somewhere.
I
There
do not
we
have
go.
Robinson.
We don't have Robinson.
Don't have Robinson.
We do have Robinson.
We have Robinson.
Okay. Do you want to skip to someone else in case he finds them, or do you want me to just go?
Yeah.
I can just go. Whichever.
Yeah.
Okay.
Do you have Jennifer?
Go ahead.
Yep.
Okay.
I can buy you some time.
Okay.
Okay, yes, that is me. So thank you for coming in. Thank you, Artemis, for organizing this and for your help with the Mars Desert Research Station. I'm proud to say I was on Crew 1 of MDRS and then commanded a crew later. So that was a fantastic experience. So thank you for allowing that to happen. So I am a planetary scientist by training, and so I do a lot of analog field work in order to understand mostly planetary geology and astrobiology on the moon and also in Mars especially. So I'm very fortunate, I think, in my career at NASA that I've been able to go to various places on Earth that I would have never been able to go to before. So I've been able to go to places like Antarctica and the Arctic and Svalbard and Iceland and Utah, the Atacama Desert, all these different places that are analogs for mostly Mars because of some attribute, like Kim was saying. You have your research question. Maybe you need to go somewhere that's very cold or very dry or volcanic or an impact crater site. Whatever your research question is, that's what drives you to those places. So I just wanted to give a little overview of why we're interested in doing this from the planetary science side of things. And as we go into moon, into deep space, to Mars and beyond, we'll have new operational paradigms for how we conduct human spaceflight. And so where I'm coming at is when we get to the surface of Mars, and we go from that survive phase to the thrive phase, right? And what those astronauts are going to be doing is planetary science. You're going to go out, you're going to learn about Mars. You want to understand the planet. So decision making when we're doing that will be at a different cadence than is currently experienced during space exploration. We've heard a lot during this conference about crew autonomy, decision making, and the ability for the crew to go out and to do these tasks. And in this case too, with science and discovery as key drivers. What are the operational concepts, the EVA types, and support tools that are going to be successful to enable us to optimize that science and exploration on the Martian surface once we send people there? So that's where we're coming at. We want to optimize the science once we get to Mars. So one way of doing this, of course, one tool in the toolbox is going to these research analog sites. And so when I talk about an analog, I'm talking about places on Earth that allow us to approximate operational and or physical conditions on other planetary bodies and within deep space. And again, it's all driven by your research question of what you're trying to answer. That's what drives what site you go to. And so when we're putting together these analog campaigns, so I've been lucky enough to be able to lead a lot of these teams. We have teams of, scientists, engineers, astronauts, all going out into the field to do this work. For our work, it's grounded in the science. Scientific investigations focusing on outstanding planetary science and astrobiology questions. We're never simulating the science that we're doing. When we go out, we're always learning about that volcanic field site or what that impact crater means to Mars or how you understand habitability in a volcanic terrain in Hawaii as an analog for Mars. Always doing real science, writing peer-reviewed scientific papers. Graduate students need that data to get their PhD dissertations done. It just increases the fidelity of everything that you're doing. And then layered on top of that science, then we add in the science operations and the technology components. And I'm really glad to have our JSC friends here because they're the experts in this, so it's really great to have their perspectives. So for science operations, conducting the science that we're doing within simulated exploration conditions and identifying the concepts of operations for both robotics and humans working together to enable scientific return and discovery. So we're trying to figure out, how are you going to actually execute these campaigns? And then the technologies that you need in order to do that. So going out into the field is really great because it's a low-cost, relatively low-risk environment where you can test out a lot of technologies and tools. So what we do is we incorporate these into our scientific investigations to test them out for optimizing the science. So things like mobile science platforms, bringing your tools with you, bringing your samples back so you don't have to carry everything. EVA informatics, like what do you need to know when you're on EVA, like what you need to know right then and there to be able to get your job done. Display technology, so you can see what's happening, what else you need to know from your other EVA partners, what's happening in the HAB, back on the Earth, etc. Communication and navigation packages, that's always a huge deal when you've got folks out on EVA. Remote sensing, how does the remote sensing play into the current operations, also the pre-planning for where you want to go, where your traverse paths will be, et cetera, et cetera. Advanced mission planning tools, scheduling tools, timeline tools, right? You've got to stick to the schedule and make sure you get your tasks done. Sometimes you have interrelated tasks when you have maybe a robotic asset doing something that's dependent on what the humans are doing and having that all line up. And then scientifically relevant instrumentation packages. So we bring handheld field instruments, handheld lib spectrometer, a handheld field portable visible near infrared instrument. What are the tools that you need to do the science and what can you bring with you to do that? So we try to always ground it in science and then layer the ops and the technology on top of that. And just so that we're all on the same page, some of the high-level operational concepts. So when we're thinking about doing the Mars case, you'll have astronauts out on EVA, that's your extravehicular activity. So these are the folks that are out doing the exploration and doing the sampling. Then you will likely have an IVA crew as well, intravehicular activity. So this is, sort of think about it at your Mars base, in your Mars habitat. You're going to have the rest of the crew. Maybe you have science support in there. Maybe you have laboratory support. And they can be in direct comm with the EVA team. So what is the interaction between the people that are on EVA and the people that are in IVA, right? Is there science support coming from there? Which samples to collect? Which site to go to next? How's your timeline doing? You can have that direct comm. Because then when you get to Mars, if you have mission support back on Earth, you've got the time delay to deal with. So this is where, all the communications and the data flow, it's very different from how we have done field geology, on the moon, for example, in the past. So there are a lot of different levels of, communications flow and who talks to who and what data gets sent back, and you've got bandwidth limitations, and how do you integrate this all to optimize the science? And then I just put in a few pictures of just to give you a flavor for some of the types of work that I do and that we do within the Planetary Science Division. Here's in Iceland just last year, testing field portable instruments. We were out in the volcanic terrains there. There's in the Mojave Desert, we did a rover deployment as an analog for mapping out water ice in support of ISRU, in situ resource utilization. So we need to ground truth that ice. I think we heard that theme throughout this conference yesterday and today. Map out that ice so that we can know where those reserves are and what the characteristics are to use them for ISRU. In Iceland, doing UAV test flights, our team from NASA Kennedy are experts. When there's terrains we can't access, on foot with people or with rovers, you can use aerial assets and mount instrumentation on there. Down at the bottom, this is one of the science operations centers. This was supporting one of the rover deployments. So when we send these rovers to the moon or to Mars, right, we don't send the entire science team. The science team is back and the operations team is back on Earth. So we simulate this. We send the rovers out into the desert, and then we keep everybody else back at the NASA center, and everyone's in this mission support or mission control room and executing the mission that way with the instrumentation on the rover, getting the data back, coming back, analyzing it, writing the papers, and figuring out what ConOps work the best. There's Antarctica. And then in the middle, I also wanted to point out that doing this analog work is a really great way for public engagement and student support and teacher support. So every time we go out into the field, we always make friends with the local community wherever we are. This is out in Arco in Idaho, which is right near Craters of the Moon National Monument and Preserve, where we do a lot of field work. So Here's student involvement. We had a team of undergraduate students. We helped them write this grant, and they won, and they developed a high-altitude balloon, and they put payload instrumentation on it and flew the balloon, collected data to support our field work. And so it was a great experience for them to work hand in hand with the NASA team so that they could actually do science and then do the technology and the deployment. And then also, we always run a program called Spaceward Bound, which was started, I think in Ames by Chris McKay, many years ago. And I guess that's a sign of a good program that it's still going and people are taking off on it. So we always team and bring teachers in through the state space grants wherever we are. And they send teachers out, and we work with those teachers before the deployment. We teach them about the science, what we're doing, get them involved. They come out in the field with us. They work side by side with us. I mean, they get to carry just as many rocks as we do, right? So they take data with the handheld field instruments, they are involved in the science discussions, and then we follow up with them after, and we keep them involved in the analysis. They've been on publications with us, with the science team, conference proceedings, et cetera, et cetera. And then they take that information and that enthusiasm back to their classrooms and back to their communities. And so we track what they do, and they go back and they inspire their students, and they give seminars to their students, and they develop new lesson plans, and they give talks at their local community centers and at the libraries and the science museums. And so it's just a way to share the excitement of what we're doing. And as Alexa, I think she's here, was talking about yesterday in the panel, that experiential learning for both teachers and students to have hands-on, practical experience doing these types of investigations. So we try and do that as much as possible. And that's my last slide. That's just Iceland, because these are just some of the beautiful places on Earth.
Okay. Technical support. Did you find Julie Robinson?
Give me 1 second. I have it.
Imagine a delay from Mars. It's
This is a comm delay.
22 minutes. I always say, imagine you're on Mars. There's a 22-minute delay one way. So now you tell Houston, we've had a problem. 45 minutes later, you hear, say again. You gotta learn to.
I'll start.
Well, there you go.
Yay! Okay. So, as I mentioned then, there are a number of ways, of course, to simulate the exploration hazards here on Earth. And we think of those as being, there being 5 major hazards of human spaceflight. There's the gravity transitions, there's the radiation environment, there's the isolated and closed conditions, there's being in a hostile closed environment, and then there's the distance from Earth itself. And you can simulate different parts of these in different platforms. So for example, we have the NASA Space Radiation Laboratory, where we do primarily work focused on simulating galactic cosmic rays, because we can't get those on ISS in the Earth's magnetosphere, and we really want to try to understand what a deep space radiation exposure, either in transit or on the surface of Mars or on the surface of the Moon, might be like. For altered gravity, we can do everything from head down tilt in facilities like NVHAB here, or in the zero-G flights. Also for isolation and confinement, we work in a variety of analogs, including HERA and NEK in Russia. And to simulate a hostile environment, you can work in places like Antarctica, where we collaborate with the National Science Foundation to study the behavioral aspects of overwintering in a dark, cold, isolated, dangerous place in Antarctica for those overwinter crews, for example, at Palmer Station. If you look at those then across the different mission analogs, this is a kind of a cartoon view of those 5 different aspects of hazards of human spaceflight and how you might do them. And the little cans on the bottom are things you might do in a ground-based simulation on that planet or on that body. And then you can see there are little vehicles in orbit to show things you might do in an orbit-based simulation. So on ISS today, we are particularly able to study altered gravity and the hostile closed environment. But with modification, we could study isolation and confinement and distance from Earth. And I'll talk about some things we're doing that way shortly. Similarly, as we get to Gateway, we can look at altered gravity, hostile closed environment, start expanding the radiation exposure, and start looking at distance from Earth, because in a near rectilinear halo orbit, you have times when you're actually quite far out in the Earth-Moon system and other times when you're closer in. A Mars flyby, should one occur,
then you're starting to look at altered gravity, all of those components together. But of course, as we look at lunar surface activities on the bottom, then you've got partial gravity, you've got a hostile closed environment, you've got radiation, you've got confinement. And then in the ground simulations, which many of my colleagues here are talking about, you can get the isolation and confinement. You're really having to simulate coarsely some of the other things. And that's one reason why many of the ground-based simulations tend to focus on the Mars surface activities in the middle of a mission, your geological type activities. So what I'm going to talk about today are some cases that we've developed for the use of ISS as a deep space analog that have been approved and are going to be executed in the next few years. And really they're focused on testing our operations procedures in medical care, the isolation and confinement effects of a deep space transit, and also the surface operations after physiological deconditioning. So I call this the golden first days of landing on Mars. So one of the things we've learned from human spaceflight on ISS is that some of the most vulnerable times are launches, landings, and dockings. Those are times when things can be more dangerous, when the crew needs to be on their toes and able to respond. And one of the things we know from ISS is that when the crew is deconditioned after a long period on ISS, those first days as they come back to a gravity environment are some of the ones where they have the most difficulty in being able to carry out mission tasks. And so we're focusing on some of those aspects that we could do from ISS. This began 2 years ago when we identified that there were a number of things that scientists would like to do using ISS as a Mars analog, but that were not easy to do with the current way the program was structured. And I had the opportunity to lead a Tiger team that included crew office representatives, flight directors, and so forth to come up with a set of use cases. And there are 3 that we brought forward that have all been approved for various sorts of implementation. The first use case is doing autonomy and crew medical care in 1 to 2 day simulations. And we have a quick start on this in 2019 where we'll be doing a simulated medical event happening on the ISS where the crew has to operate autonomously without any help from the ground. So in other words, they're not going to say, "Hello, Houston, we've got a problem." They need to have the tools and the knowledge on board to solve that problem themselves without support from the ground. We're also implementing a comm delay capability that can be controlled and used on the ISS. That begins in September of this year, and then that can be incorporated into a wide variety of autonomy tasks and simulations to happen in the future. A second use case is to take advantage of the fact that a 6-month or longer ISS mission gives you the level of deconditioning that we would expect a crew member that had just transited to Mars to have, and use ISS landings as a simulation for that golden period upon first landing on the surface of Mars. Some of our vehicles, some of our commercial crew vehicles will be landing in the water, the SpaceX vehicle, and that's not very predictive of Mars, and in fact that adds an additional high level of disruption to the crew's sensory motor system, and so that's not a good Mars analog. But the Boeing CST landings in the desert are excellent surface analogs for a Mars landing, and we've been doing 10-hour tests in Kazakhstan in collaboration with our Russian colleagues for a number of years and found that the crew is significantly disrupted in that first 10 hours. So the question is, what can they do operationally and what's the distribution of human variability in the first few days on the surface of Mars so that our mission planners can plan something that is operationally realistic? One of the great advantages of this is this becomes something that our crew members, as the consummate professionals they are really interested in documenting. They want to be sure that they'll be able to execute the mission as planned, and so this becomes operationally driven to the point where crew members are willing to forego, even having been gone for 6 months after having trained in Russia or other places for several years, and then when they land, they're willing to give up additional time to do these kinds of tests in this kind of a simulation because it's really about that critical operational phase someday. And our third use case is autonomy with isolation and confinement as we switch out from just 1 to 2 days for a medical event to extending that to a 2-week communication delay. The program's agreed to do 2 weeks. That's a balance between the disruption of all the other commercial research that's in queue. We have a pretty big backlog on the International Space Station of researchers waiting to get their research done. So we don't want to just disrupt it. Some people people will say, well, why don't you just close all the windows and comm delay it and just let the crew sit there for a year? And the fact is you would make about 10,000 people very unhappy by doing that because they've been in queue waiting to have access to the ISS as a research platform. But what we can do is look for good windows where there aren't dockings or other visiting vehicles and push our simulation experience from that 1 to 2 days that I talked about already to a 2 to 3 week time frame. And then as we collect data on that, what the effects of that isolation and confinement and the struggles in doing things autonomously for 2 weeks, that's a significant operational experience base for our mission controllers and our crew office that have never operated in that way in the history of human spaceflight. Then you take the lessons learned from that period of time, and then NASA can evaluate whether 30 to 45 day comm delayed, isolated, and confined missions on ISS would add additional operational value. So we have a progressive kind of approach to these different use cases, but they also help us to gain really substantial operational experience that is relevant both to the lunar surface as well as to Mars. That's all.
Well, Natalie, you're the next one.
Okay, I'm Natalie Mary. I work with the Extravehicular Activity Office at JSC. So I am a systems engineer, but there's some people skills. So I do not have any charts for you today, but I can talk from the engineering side. And so what we're working on right now is the next generation spacesuit. So right now we have on ISS the Extravehicular Mobility Unit, and it was really built and designed for shuttle and then upgraded for station. So one of the things that we're really looking at is an exploration EMU, or what we call currently the XEMU. So we're working on that, and we're going to be, we're actually in the middle of our design process with systems engineering. So we're coming towards our preliminary design review for a demonstration unit for the XEMU, which we're actually going to demonstrate on ISS. And then we'll be able to upgrade that suit and have it be a partial gravity suit, in turn using it on the lunar surface, and then upgrading for the Mars environment, which is different gravity, different environments such as the CO2 atmosphere, the convective thermal versus radiation thermal. So it's those different upgrades that we can do throughout the years. And one of the things that we really heavily do is work with the scientists and the geologists and make sure, and the vehicle systems, to make sure that our suit can actually perform and be built towards the requirements and operational concepts so that we can actually do the work and kneel down on the lunar surface, pick up your instruments without falling and getting dust everywhere, fix a vehicle. And so in order to do that, we also start with the analogs and work with the scientists and systems to be able to come up with our requirements and our operational concepts that we actually put down on paper. So there's a lot of paperwork, a lot of documents that we go through that are then fed down to the engineering teams that are actually doing the designing of the suit to meet those requirements and make sure that we can perform those operations. So one of a couple of analogs that I've been on, I haven't been on a lot, but I got to go out on a field geology trip and coming up with the requirements and operational concepts for the new suit. It was eye-opening to be able to go out with them and see exactly what you have to do as a scientist in a suit. And so, of course, we were out there shirt sleeve, but the terrain can be very difficult to navigate. And you don't want to just go to the edge of a rock formation and pick up a rock. I mean, sometimes you do. Don't let me speak for you guys.
Yeah, no, you're good, you're good.
But sometimes you actually want to go up and climb into the rock formation, take your hammer and chip off a piece and see what samples that you like, what samples they need as scientists. A lot of times you're talking to the science comm in the mission control room. You're talking with Capcom. So there's a lot of backroom discussion going on. And then with a comm latency, such as Mars, if you've got 22 minutes of a comm latency that you have to be able to discuss the science that you're picking up, making sure that you're optimizing exactly what the scientists and folks want, then you've got to probably have some kind of IV or intravehicular activity workstation that will help enable that. And so there's a lot of optimization there on trying to figure out exactly what information that you need that IV crew member to help the EV crew member feed, and what exactly you can use to feed into the suit informatics. So what do you need on your heads-up display? You don't want too much information. You need the right information. You also need to make sure that your EVA suit is getting the right suit information. So what's your oxygen level and things like that. How much farther can you go and get back to your rover or something like that, so that you can have enough time to perform the actions that the SciComm wants you to do. And then there's so all of that informatics. We're talking about AR, being able to have the IV workstation crew member be able to go through procedures with you, with the EVA crew member, so that you don't have to rely on the ground all the time, that you can have that autonomy during that large comm latency. So we're looking at a very different perspective, but we have to have all of the input from the geologists and scientists in order to make the right suit to enable that science and the lunar surface and Martian surface. And so we also do use the NASA Extreme Environment Mission Operations, which I get to go on for the first time next month, and I'll be working as a flight controller topside, but this is using the Aquarius Reef Base off of Florida. That's an underwater habitat, and they've got 4 astronauts. Some of them are ASCANs or astronaut candidates. Some of them have been astronauts, and they can be from ESA or JAXA or actually scientists themselves. And so we simulate EVAs from that habitat, and they go out underwater performing actual science, marine biology, setting up coral reefs and things like that. And then we also have them looking at tools, like you guys were saying. There's tool carriers, there's tool harnesses on the suit, and things that we need to actually get the tools designers and engineers to make for the suit. So we're looking at all of that: IV, tools, operations, communication, and so we pull all of that information from the analogs and try and put those into our documentation for the concept of operations, and thereby driving the requirements for the spacesuits. Then once we get into like the design phase of the spacesuit, then we up in our fidelity to testing in NASA for like gravity offloading of the suit to see how you perform in the suit, and then eventually training in the neutral buoyancy lab, where your astronauts and ASCANs and suit designers are actually in the suit and the neutral buoyancy lab performing similar activities. So there's a whole end-to-end process, and it starts with analogs, making sure that we've got the right concept of operations to perform on the gravities.
Okay, well, I have given it some thought, of course, what I want you to answer. And the first thing that comes to mind now with this idea that in 5 years' time we'll be on the moon, for me it's still in 14 years' time we will be en route to Mars to land there in October 2033. What is the technology that needs to be developed right now, because it will have a long lead, the long poles we always call them. So what you need really to start working on right now to be able to say, okay, in 5 years' time we will have this ready, test it, really, well enough that you can fly it to the moon, let alone 14 years from now to Mars. Each one of you, I start with you, Julie. What do you think is something that really needs to get started right now, or this whole talk of going to the moon and Mars is good?
So I think a couple of things that we have big concerns about. One is our radiation shielding approach, both in transit as well as on the lunar surface for both events as well as galactic cosmic rays. A second is our food system, because a food system is a significant mass driver for the first trip to Mars, and those technologies are evolving quite rapidly here on Earth. But if you've seen some of the pictures of some of the plant system ideas, those are not packageable, portable, or small enough to take to Mars. The third thing is a crew health and performance system that is fully integrated with the vehicle so that it supports your autonomous medical system. And that's something that we are scrambling to try and get done in time for the Gateway. It certainly won't be between now and 2024, but it may be added when we add the US HAB to the Gateway. And if we do that right, that's our Mars forward system, but that hasn't been designed or built yet.
I hope you won't threaten physical violence if I say everything, because the reason I say that is somewhat seriously is that the integration stage is so important. So a mission to Mars or to the Moon is a system of systems, and one of those subsystems, or several of them, are the human piece of this. So until you've integrated all of the various pieces and tested them over long durations, hard use, put away wet or put away dry and dusty, then you won't know where the failure points are, no matter how well you've tried to anticipate them. So I think that's one of the challenges of a short timeline, is getting all of the pieces in place so that you have a chance to integrate them and test them hard before they go. And that, by the way, is one of the things that analogs are good for, is hard testing integrated systems.
Yeah, I concur with Kim on the everything comment. But then also for the surface operations and for doing field geology and astrobiology, we want to figure out, did life ever evolve on Mars? And we want to answer that question. And we're going to need people boots on the ground on Mars to really attack that problem. So I actually think a big deal is the suit, for having humans out there in the field. Once we send humans, our robots are fantastic and we have learned so much, and we have been able to narrow down where to go, where not to go, follow the water. We have a very robust robotic Mars program. But once we get the humans on the ground, we are going to learn so much more about Mars and have so many more questions. And we can't do that if we can't be functional in the suits. And so even looking back at Apollo, one of the biggest feedbacks was the gloves, right? The gloves were so hard to operate and to work with, and their hands were sore, and they couldn't do everything. And so we make these plans and these con-ups for what we want to do in the field, the measurements we want to take, the type of sites we want to visit, the outcrops we want to go to, the samples we need, but none of that will happen if we don't have functional suits. And that's why it's so great to have the suit folks, right, so integrated in understanding what the science needs are, so that they can say, okay, we're going to go and design something to make that happen. And so it's really important within NASA to have that exchange, that interplay, so that we can make this functional.
Yeah, thanks, Jen. That's exactly. You just really answered it for
sorry.
me. No, but it is. It's great. We've taken all of the Apollo lessons learned to build off of that and also dust mitigation, which is, it's dirt to me, but but it is very, very important for the crew health and making sure that you meet those requirements in your habitable volume, not to bring all of that back in. And so we're working with all of those types of lessons learned, including the mobility and the dexterity of the gloves, being able to kneel down and not just fall down and not be able to get up, and hammer and pick up that hammer. And that mobility is a key aspect of one of the things we're working on, especially in the lower torso assembly with the bearings that we've added in, which does increase mass, but it also increases your capability to be able to pick up that rock or look more closely. And then and actually more mass can help you also on the lunar surface. One of the things that they did have a problem with was getting down to pick something up. And so that extra mass might help you a little bit on the lunar surface. The Mars surface we'd need to upgrade from there to make sure that we're not too heavy on the Mars surface with a Martian suit. Another thing that we're really looking at is the informatics. Like I said, I think that'll help out a lot with the data points, the timing, the audio, and all of that. So I don't feel like we're a long pole since we're already incorporating those lessons learned into our current suit design. So we're really working on that and are pretty proud about how far along we are. As for the long poles, I think some of it has to do with decision making on some of the ops cons and what are we going to actually do and what is our architecture going to look like at, by 2024 and 2033 to get to Mars. And so want to make sure that we're not boggled down and optimizing everything to a point that we're not making decisions along the way to get there. So
Fair enough.
I think we can do it though.
Fair enough. What was also mentioned already in this round is systems integration. And I know that people that are completely not in the know always have the feeling that it's either robots or humans. Anyone who has been involved with Mars analogs know that even here on Earth, the idea is it will be both. The robots will do this climbing to the rock face because we are sure as hell are not going to risk one of 4 or 6 astronauts falling down if we can, risk a robot. Not good to lose the robot, but, magnitudes not as big a problem as losing a human being. How do you feel that we are getting on right now with this, also building these robots that will, lighten our tasks, do the things that are dangerous or even the things that are repetitive, so they free up time. Are we working on that?
I can. Yes. And this is a great place. Terrestrial analogs are a great place to test this because I think there's 3 phases where robots will be used, and we're testing each of these now. First is before the human EVAs. So we're doing this now. We send robots into the field, whether it's a rover, whether it's a UAV, whether it's remote sensing that's collected from an orbital asset, to understand your field site, do that initial recon, plan out exactly what your humans are going to do, plan out their traverse paths, and have that all scheduled out and get that initial primary science data to drive your science questions. Then there's the phase where you have humans on the ground, and so you've got robotic assets helping you in various different ways, doing the repetitive type work, doing some of the more dangerous work, carrying equipment for you, carrying tools and samples, and being a mobile asset with you. Making measurements that humans can't either reach or do or might be dangerous, whatever it is. There's a whole slew of things that robots can do to assist the humans. And then once the humans have left that site, you've got robotic follow-up, right? Because every time we go into a field site, even if you've been there before, you always learn something new and you come back with new questions. And time again, you just don't have time when you're in the field, whether it's, you're doing terrestrial analog work and you're there for 2 weeks and you got to fly home, whether you're on the moon and you've got, limited time, you're on Mars, your time is very valuable. So you have robotic assets that then can go that are equipped with the instrumentation that you have decided that you needed or you knew you needed to go back and do follow-up work. So there's sort of 3 phases, and we're testing each of those in the field.
If I could just add, I think that robotics is something that's evolving rapidly on the ground, and we'll actually be able to leverage a lot of the technology development on the ground in the next 10 to 15 years for our eventual Mars surface operations. Where I think we need to stretch our minds and our concepts of operations more is in the way we use autonomy and smart learning and onboard systems. So right now we're very locked into a ground communication approach, and we're locked into that even when we deploy our robotic systems in space. So we need to have a more localized version, and one way I like to describe this is think about how differently you operated 10 years ago before you had an iPhone, and how your relationship with critically needed information has changed. You don't carry around, you don't even buy books anymore. You carry around something in your pocket, and you don't have to have it stored locally like you did 5 years ago where you kept everything on your laptop. Now you just Google it, and we essentially need our robotic systems to be blended with our automation systems so that the information is there rapidly, just in time for the crew members for a variety of situations that haven't arisen before. And developing those smart systems is linked to robotics. It's definitely how high-end robotics is evolving as well, and we'll need to have those 2 flows of technology come together to make us successful on Mars.
Okay. Anyone else want to? Okay. a follow-up to this. Will I have a kind of Alexa if I'm on Mars? I mean, will I say, whatever name I give the thing, robot or computer, tell me, what's the weather in the next 5 hours? How is my heart rate doing? Instead of going to in the heads up. Will this be integrated? Will there be a HAL 9000? God forbid a SAL 9000, but a HAL 9000. I know IBM would be interested, or they were for a while, in developing Watson for this. Do you think this will happen, or will it still be more clunky like we do it now on Earth?
So we are actually working with IBM and working on Watson implementations plus other AI implementations. I think that the way that I see those technologies going is even more dramatic than Alexa today. Alexa's pretty kludgy. And in fact, what it will be more like is a heads-up display that tells you information you need before you know you need to ask for it. So when I talk about an integrated crew health and performance system, it's going to give you a warning that your heart rate's getting high before you know to ask, hey, why am I feeling a little out of breath? Do I need to stop this EVA? And those kinds of integrated systems where the vehicle itself is monitoring the operations as they occur, and part of your safety net is very different than the way we operate today. And many of those systems are relying on machine learning and other kinds of approaches that don't fully exist today and are also evolving quite rapidly.
Yeah, there's along those lines, there's some interesting work at MIT going on right now for planning out EVA traverse paths and optimizing those paths based on human performance, like heart rates and respiration rates and whatnot. And so you need to get from point A to point B, and it will calculate what is the best way to get from point A to point B, which is not always obvious. And then monitor that schedule-wise and from the human physiology standpoint and make adjustments in time that you didn't even know that you needed to make, but it is ahead of you, and it knows better how to move you from here to there for moving about on the surface. So there's some interesting work that's going on in those realms.
May I add one more, which is tied into the behavioral health and performance issues that we were just talking about. Mission support, you don't want mission support to be relying on self-report. I mean, astronauts are fairly introspective and fairly honest, but you don't want to wait for someone to have to say in a report, I'm starting to feel a bit depressed and anxious, or I'm not getting on very well with this other crew member. Because if you wait till that point, it's probably almost too late. So instead you want automated systems that are able to start to detect the warning signs of those kinds of issues coming up. And that we've tested some of those systems at HiSEAS, but I think it needs to get a lot more sophisticated so that ground control or mission support, whichever you want to call it, can start to see the yellow flags before they turn red.
Another robotics point, because you guys have actually talked about some of the suit stuff. Yes, we definitely already have requirements and ops cons to make sure that we're not going too far based on our life support system, because it is limited to 8 hours, depending on your met rate. But another thing that we were talking about with our con ops is the planetary protection aspect of Mars, and sending out a special rover into special regions that the humans may not be allowed to go just yet because of that planetary protection aspect, reverse and forward contamination. We don't want to have to, we don't want to get out there and contaminate the very samples that we're picking up and somebody look at it and be like, oh my God, there's life. But in fact, it was, our suit venting into the, so we have specialized rovers that we're talking about having, as well as sample containment and things like that, and being able to speak that in the informatics.
Okay. Several times during these answers or your presentations, either you called it control or support. And I think from my experience with being a mission director for the Mars Desert Research Station, there's no such thing of people that are 100 million kilometers away to control them. I'm on Mars, come and get me. What are you going to do? Deny me re-entry onto Earth when I come back? I don't think so. So what do you think you need to learn? Same, because this is also interconnected with the fact, if I simulate things on the moon, I have to be cognizant that I shouldn't then, whisper in the ear of the astronaut, which I could because it's 1.25 second delay, which I still can tell you, pick up that rock that I just saw through your camera. What's your take on it all? Is it mission support? Is it mission control? How much autonomy are we going to give those humans on the moon, but especially on Mars?
So I feel like based on some of the analogs that we've done, and some of the actual that we've used on the ISS, we've done a little bit of comm latency on ISS, is that it's going to be an implemental change over time. And I think we're going to learn from not only the analogs that we do, but once we do utilize ISS more, we can utilize the lunar surface more to understand that 22-minute comm latency for Mars. So I think that it's over time we're going to get to that point where we get more and more autonomous, our systems get more and more autonomous, and our crew members get more and more autonomous.
Yeah, I think control is one of the places where I feel like some of our ground analogs actually fail us, because those are highly controlled in the same, and the controllers are influencing the experience of the people inside. Now they're doing that for a reason, but that means it's about like reality TV in its realism for what the crew knows that they're really on their own. So it is psychologically different. And I think that as we move towards Mars missions, we're going to need to have systems in place so that the crew could be fully autonomous if there is no ground connection, both as a contingency situation because of dust storms, because of other situations. So we have a long way to go to get from the operations that we're comfortable with today, and today we would safe a system before a situation like that happened on Mars. Well, you can't safe a living habitat full of humans and have them just go into torpor and wait until everything passes and communication can be restored. So we've got a lot of work to go there, and we have a mission support culture that has been amazing at solving problems on behalf of the crew. We need to actually have that mission support be part of the crew so that they're able to make those decisions with the information that they need without us.
I really agree with everything I'm hearing here, that the latency, the distance, and also the length of the missions is going to require more crew autonomy. But who here has seen The Martian? Awesome. That makes my life so much easier. So one thing that you've seen from decades of psychological research is that highly cohesive teams are high performing. There's a correlation between cohesiveness and performance. Not surprising. You got a group of people who get along really well, who work well together, they're going to perform better. However, highly cohesive teams also tend to be more autonomous in their decision making, and that speaks to what Artemis was saying. If a more cohesive team thinks they should be doing something in a different way than what they're being told from Earth, they're more likely to go their way. So I think you see that in The Martian, where you've got this very high cohesive, highly performing Mars team, and what do they do halfway through the movie? They mutiny. They do the exact opposite of what they're being told to do. Now, I don't think a team of NASA astronauts are going to mutiny on Mars. That's obviously overstatement for the sake of drama. But you are going to see some of that independence, both in a positive sense and possibly in a negative sense. So I think that's something to prepare for and plan for and sort of build organizational structures around and be ready for it, because I think we can expect it.
And just one more note on this topic is that, this is part of the reason we're sending humans, because it was Lori Glaze yesterday, who's the Planetary Science Division Director, was saying, humans with our eyes and our brains are the best computers that there are. And so we can take in a scene and we can synthesize and analyze that data and make decisions more rapidly than any machine that we have. And so we want to capitalize on why we're sending people, so that they can do these types of tasks. And so that's one of the things that I've learned doing these analogs, being on both sides, being the person in the field, right, with that situational awareness, and being back in the mission support area where you've got the best cameras, better bandwidth than we currently have for Mars, more downlink. You think you know the site, you think you know the field, but you don't, because once you get actually there with your own feet, boots on the ground, you have a completely different perspective. And so it happens all the time that, you know, for the mission support, we say, oh, drive the rover over there. And they're like, why? Are you crazy? Like, that is exactly where you don't want to go. And like, but it looks great on my screen, you know, and then if you're actually in the field, you have a completely different perspective. And so that's what we want to capitalize on. And so that goes back to more autonomy and having the tools and equipment for the crew to be able to do that.
Okay. There is still, I think, some time. I mean, I'm willing to forgo a bit of tea. Or coffee. Question.
Yeah, I have two quick questions. One for Julie Robinson. I think you said about the 2-week communication delay test on the ISS. Is that going to happen? I'm not. Is it scheduled? Oh, sorry.
It's a question about the 2-week communication delay for the ISS. Is this something that's going to happen, and if so, when? And just a quick question to Natalie, Mary. Is your suit going to be ready for the astronauts in 2024 who are going to walk on the moon? So maybe Julie first.
Okay, sure. So it is going to happen. We are doing some 1 to 2 day simulations first, and including gradually adding comm delay to those simulations. Then we plan to go to the 2-week case and do a couple of runs of those, and those would start in the 2022-2023 timeframe.
Yeah, and we're actually farther along than most of the, if not all of the surface systems. So we're almost to PDR with our XEMU demo, and the upgrade, which we've already tested, like in the NBL, to the lower torso assembly would be like a delta PDR. So in systems engineering's terms, so we're doing really well with the suits, and I think that we can make it by 2024 with the right amount of funding. Folks,
Okay.
everything, yeah. So, but
Okay.
we're farther along than most.
Okay, I'll
everybody
go to
else,
the
so.
and ask for another billion.
Yes.
Roll.
Yeah.
Should I wait for a microphone?
Yeah, the microphone.
Yeah.
Yes.
Yeah, I had two questions. First, I've been pulling on a thread about the microbiome and the interactions with the humans between, and I didn't know if there's any analogs that had taken into capacity that. And the second one was, when you look at the lunar dust and the spacesuits, the component of like electrostatic or any sort of charge, I noticed a lot of the spacesuits came back with tons of the lunar dust on. Is there any sort of mitigating efforts for that, as well as for radiation? And then about conflict resolution, a thread that I've been pulling on is mindfulness in space, since we did our yoga therapy for space health a few years ago. So any thoughts on that?
So the quick answer on microbiome is yes, we do look at that in appropriate analogs. Analogs vary in their degree of closedness, so that means they also vary in their fidelity, but it's an important piece to look at, and we definitely look at it on ISS as well. Actually, not just GeneLab, but also in the crew microbiome, and then how that's interfacing with the habitat, and then what happens when you have things like rodents and plants on board as well.
But is there simulation back on Earth?
Yeah, we're doing some of that at HiSEAS as well.
Yeah, it's done in a variety of the analogs on the ground as well, in the Aquarius and other places.
And right quick for the dust mitigation, yes, we're looking a lot at the Apollo lessons learned and have requirements in place for that, some of which is based on the human systems and how much is allowed back into your habitable volume. And so another thing would be like zippers or pockets, things that actually collected more dust than just on the outside of the suit. And then also looking at technologies in order to remove that suit, such as wands or things like that. So there's actually a lot of folks trying to get together right now to come up with a group of folks that can revitalize that end-to-end layered engineering defense between once you step out the door to ingress into your habitable volume, and then so everyone would share the pain in a way, but we're definitely incorporating a lot of those lessons learned.
Is the thing because of electrostatic at all? Or?
I'm sorry?
Big thing of the dust.
Yeah, so that's what we've heard, and so we're working with some folks to see how we can utilize that aspect
By repelling it?
by repelling it or using some kind of wand to repel it or to. So I don't think by 2024 that we quite get to that point where our suit can just like, pop off all the dust.
Okay.
But it's something that.
With the microphone?
Yeah, you.
Sure. Yeah. I'm interested in knowing more about the initiatives that you already have in regards to the psychological and mental health. As a mental health practitioner, I mean that's the first thing that always comes to my mind. Like, what are the initiatives that are already in place, and what more has to be done in order for this to happen, obviously successfully, and be able and be sustainable.
Shall I? Most of our research at HiSEAS is focused on crew composition, crew cohesion, and crew performance. So those are behavioral health and performance pieces, but a lot of different sub-projects under there. I think one thing that maybe it would have been nice if we were able to say to NASA at the end of this, look, if you just keep personality type X off the crew, or take this measure or that measure, then everything will be fine. But we can't say that. Instead, what we've seen is that each crew has its own conflicts. And they're usually special to the crew, so you're not just preventing kind of conflict A or type of conflict B. Instead, what you have to do is you have a crew that's made up of the individuals who are resilient, but also a group that's resilient as a whole, so that they're able to have these conflicts, resolve them to the extent possible, and then return to a high-functioning state afterwards. So I think that's quite important, and both composition plays a role, but support also plays a role. So being able to sort of detect these issues, as I said earlier, before they become very serious, alert the crew to them, and give them the support they need to respond well to them is vital. And I think that overlaps to some extent with the medical care considerations that we're doing as well.
Just to add to that, on ISS today, we have a behavioral health and performance system that includes behavior. And we have a series of things that we do to maintain crew mood, to monitor the crew, be sure that we're using appropriate interventions if we need them. The challenge is how you would extend that system to a Mars mission. For example, every time we have a cargo flight go to ISS, we take fresh fruits and vegetables. That helps with nutrition, but it also helps with the monotony of the food system. And of course, we have a very diverse food system on ISS that's evolved as different international companies have flown things over the past few years. So each of those things, we have to understand its role in the behavioral health of our crews, and then how we would replace that in a mission scenario that doesn't support it. The other thing we have to do is be more autonomous. So it may be, today, our flight surgeons are a key line of defense. They're working with the families, they're working with the crew's talking to their families on the satellite phones on a regular basis. And that network is a big part of the behavioral support. On a Mars mission, that has to change. The crew has to be more supportive of each other. It may be that the commander has more responsibility for understanding the behavioral health of his crew member, but it also means that the way that they relate to families, the way that we deal with replace care packages, all of those things have to be modified. So it's not that we don't know the kinds of things we can do to help the crew, it's that we have to change the way that we're used to providing that support. And I think as we do that, we gain a lot of insights into the operational perspectives that we need to be successful in all these different areas.
Okay, there are 2 questions, but she might, you have another panel, she might leave us. If the other panels are okay, then these 2 questions, and that's it. Then we're going to have tea or whatever you want, right? You.
Okay. So in my view, there is a need for integration across analog activities, a need for standardization of methods that can be tested and validated across analogs. Is there a department, entity, agency looking into this, into developing standards, developing standardized methods that then could be tested, in different analogs?
Yeah, so there is an international panel that's built a set of standard measures first for bed rest studies, and then those have been extended to studies of crew members on analog platforms. So we do a set of standard measures on the crews in NEK, in Russia, on the crews in Hera, on the crews on ISS, and those measures include both physiological measures as well as behavioral measures. So that gives you the ability not only to compare and see how good those analogs are, but also to better understand where they're failing. So for example, a lot of people will think, oh, we've heard astronauts have disrupted immune systems. Maybe that's because of microgravity. But in fact, in our analogs, when they're in a closed environment, we actually see similar cortisol patterns where stress goes up, the immune system goes down, and it's really operational environments and may have very little to do with microgravity at all. So it's only by having those kinds of standard measures across all these different analogs that you can really be sure. The flip side is sometimes when we get volunteers in an analog, and I know you were a volunteer, and it's just amazing the quality of volunteers that we get, but they're still not exactly like astronauts. They tend not to have the same military operational background. Some do, but they tend not to. They tend to be a little bit younger. And so it's useful to know if the sort of parameters that we're measuring through those standard measures across all the crew members are matching between analogs like Hera and what we're seeing on ISS. And that gives you a better sense of the fidelity of that analog.
Hi, Kim, this one is for you. Specifically interested about the HiSEAS experiment and the last mission. There was some, whatever incident happened, made the crew cut it short. And my question is, what lessons were learned from that? When you have to change, when you have to adapt, what did we learn there that wouldn't have been learned from a mission that went all the way to completion?
Well, one thing when you're doing experiments with humans on Earth, you're under the overview of an institutional review board, and long story short, you can't put your crews in at the kind of risk that even a very well-run and smoothly running mission in space is going to be exposed to. So long story short, we had a crew member who, there was an accident at the habitat. It was sufficiently worrisome that according to our protocols, we took them to the hospital. They were fine. The crew very much wanted to continue, but because we needed to then review our procedures and so on, we had to stand down the mission. So to be honest, I think that incident at that habitat tells us more about Earth than it does about Mars. Now, of course, it does lead to other questions. How if there was an accident of a similar type and you weren't able to simply take them to hospital, how would you treat them? How would you decide when they could return to capacity, and so on and so forth? And I think those are questions that NASA's already considering. Does that answer your question?
Yeah,
okay,
absolutely.
Great.
Thank you.
Well, you were a great panel, and for the 1 hour and 15 minutes we didn't kill each other, so we were a good analog. And thank you all, and thank you for your good